Be very different from what you've seen. So I'm in the physical applied math wing of MIT math department, but we work very closely with experimentalists. And what I will do today is mostly talk about experiments. And the first half of the presentation will be about two-dimensional systems, and the second half about one-dimensional systems. And I thought basically we had a little bit more time, so I hope I get here and I took some slides out. So otherwise, basically, you can ask me questions in the end for more details. Good. So I would like to start with two-dimensional systems, and what we're generally interested in my group, obviously is part of our projects, are concerned with pattern formation. And what I've shown here, just at the very course introduction, are various examples of patterns. And I will talk about systems that are similar to these type of patterns, but when you look at basically here these wrinkle patterns that you see on the skin, or you look at the surface patterns of brain crawls, or also these these are mechanical patterns, essentially growth-induced patterns, and here you have biochemical patterns, here in smaller scale, so that's a story pollen. So you see there are some phenomenologically similarities, and sometimes these patterns can occur basically in these more labyrinth or linear type shapes, and then you have also these crystalline patterns. And so we are interested in basically understanding also transition between those, specifically for systems that are more of this type. And just to give you a general idea, so the type of pattern we prefer to study are those that can somehow be described in terms of higher order PDEs. And just to give, most of you probably have seen that in some format, just to very briefly explain the main idea. So if you want to describe these type of patterns with a higher order PDE, so you need in essence two ingredients. So one is you need a field, and that field should have two preferred values. So you can think of black and white, or you can think of up and down. So the way you would describe that, you would assume there is some potential. Here it's a basic polynomial form, for example, like a Landau type potential for spins or so. And if you basically, in some parameter regime, you will only have a minimum, say that would be gray, so you would have a hard time describing pattern basically in this regime. But there may be a regime basically where you put effective potential, maybe a double wall, where you basically one minimum corresponds to black and another minimum corresponds to white, or one corresponds to down or up in that form. So this gives you a means basically to distinguish, basically say two states. But what you also want is you want to have a way of creating these scales. And you can do that by essentially doing the same thing in Fourier space. So if you think about a linear pattern that grows, so here's basically something that's just a wave pattern, and it has a growth rate here that depends on the wave number. So typically you would expect that somehow the patterns that we see here, so that have a dominant length scale, would be the ones that grow basically most quickly or most rapidly in this case. So what that effectively corresponds to would be a polynomial growth rate here, or dispersion relation. And if you basically if you want to describe this type of structure, so with a polynomial, so you have to go to at least fourth order. So here's the wave number. This would be the most unstable mode that corresponds to the wavelength that you would see. In that case, if you combine these two things, or you transform that back, you would end up with a higher order differential equation. So this is basically kind of the recipe. You can derive these type of equations starting from to&lt type models, Turing type models. You can also derive these equations, and that's what I will talk about, from elasticity theory for some systems. And it's kind of nice because you have systems that have a very different microscopic structure, but macroscopically in some mean field level they can be described by similar class of equations, but the differences are encoded in these coefficients. So this is a general idea, and I will talk about one system where you can actually derive these type of equations, and this goes back basically to describing smart materials in a way. And we are particularly interested in how these wrinkles form in curved elastic bilayer materials. So there's been a long history of studying these type of processes in planar structures, or also cylindrical geometries. So we are interested in more complicated geometries, and we got involved in that project by talking to colleagues in Pedro Rice's lab. He was at that time still at MIT, he's now at EPFL. And they performed experiments basically, and I will show more details about these experiments. And the theory work was done by my postdoc Norbert Stope, who is now at ETH, and Romain Lagrange, who is now back in France. Good, so what was the problem that they were considering? So they wanted to develop surfaces that can adaptively regulate their drag, so resistance there. And the motivation came kind of from this. So this is the evolution of golf balls. So here, this is a very early golf ball, which is a flat surface. And then if you look at the modern ones, so they have these patterns here. And the story goes that people originally played with those, and then when they ran out of new ones, they kept playing with the old ones, and they had surface patterns. Actually, they figured out that these would fly farther, so they would fly better. So, and why is that? So if you have a flat surface, and you basically in a high Reynolds number regime, you get a thick wake, and that wake, turbulent wake, determines your resistance, or your drag. Whereas if you have a pattern surface, you can create a small turbulent boundary layer, and that reduces the thickness of your wake. And this is why basically we now use these type of golf balls, or if you swimmer or sprinters, or they have these pattern suits, track suits, so they are basically made with these structures. So what Pero wanted to do, he wanted to have a system that can adaptively tune between these two states. Yeah, so that was the goal. So the system they developed in his lab, and that was basically before we got involved, was to look at a soft substrate. So these balls here in a way, so they are roughly 5 centimeters in diameter. They have a soft substrate, and then they are coated with a stiff layer. And this is basically how it looks. So here's a hemisphere, and here is a vacuum pump. So you can basically reduce the pressure on the inside compared to the outside. And when you do that, basically then this happens. Yeah? So this is basically from an experiment we're moving. So you suck out air in the center, and you create a mismatch between the inner properties and the outer properties, and it, in that particular case, leads to these golf ball patterns. So just as a proof of principle, so that it works, so they took these shapes and they put them into a wind tunnel, and then they measured as a function of differential pressures, so basically the shape that they have, so the drag coefficient, and you get a quite significant reduction in drag here, so it's almost a factor of 2, which is energetically quite significant. So the reason they started talking to us was when they produced these type of balls, that sometimes they also found basically these type of patterns. They didn't quite understand why that would happen, or under which condition that would happen. So these are all macro scale objects. So the interesting thing for us was also that you find very similar pattern on much smaller scales or bifacial scales. So this is another example. This is a system which is in an abstract way similar to this, but is created in a very different way. So this is PDMS. PDMS is essentially a transparent rubber. It's very popular in microfluidics. And when you can mold that, so here it was molded in the shape of hemispheres, and then you can, for example, expose that to gas. So you, I think we took ethanol. And then what happens is some of the gas penetrates the surface and it stiffens the outer layer. So it's very similar abstract level to what was done here. And now when you look at basically these different examples, so the only difference here is the radius of the hemisphere. So basically the curvature determines here what type of pattern you see, and the patterns are kind of similar to what you find here. And you can go to even smaller scales. So this is here sub-millimeter scale. Yeah, this is a few centimeters, sub-millimeter, and this is a few microns. And you see kind of the similar patterns. So they're treated in the same way. So you have nearly 5 orders of magnitude in length scales, and you see similar things. So, but they are kind of in an abstract way also similar systems. So the way we went to try to come up with an effective model for these type of phenomena is to start from Coiter shell theory. And you see that's a quite well-established or old theory where you start from an energy function for an elastic shell. And what we did is we coupled that to a soft substrate. In essence, what you assume is that you get the shape that you observe as a minimum of an energy potential. And that energy potential is, in essence, determined by 3 parameters. So it's the Young modulus of the film, then it's by the film thickness and the Poisson ratio of the material. So we assume basically here that the substrate and the thin film, which is a little bit stiffer, have the same Poisson ratio, close to 1/2. And so the energy has 3 contributions. So one comes from bending, one comes from stretching, and one accounts for external forces, for example, from the substrate, which tries to push the shell back into place. Yeah? So, and these So if you look at these individual contributions here, for example, the bending energy is essentially, or let's start with the stretch energy actually. So it's essentially quadratic, and the deviation of the metric tensor. So you have your base shape, which is described by some metric. So assume this is a metric of a sphere, and then you have a small deformation. So everything that we do assumes we get the So, and that gives you basically the metric that you actually observe on your deformed surface. And now you assume basically that your energy is quadratic. These deformations, you need some constitutive relations here. So this is, and you can apply the same basically assumption about the energy functional for the bending energy, just that you take the curvature tensor for the undeformed reference state, so the sphere, for example, then the deformed surface that has these little wrinkle patterns on the surface. So to get so in principle you can take these type of energy functions, you can put them into a big computer program like Abacus or so, and it will find some minima. So we wanted something where we can make also some analytic progress in the end. So what we did is a perturbation expansion. So we assumed that the dominant displacement is radial or normal to the surface, and that the displacements are small. So this is basically the two assumptions that you need. And when you do that, you can actually simplify this whole energy to a very generic form, which is exactly the structure that I discussed earlier for these pattern forming models. So here on the left-hand side is just some time basically that drives the gradient descent, and this is then the functional derivative of your energy. And what you have here is this local term, you see, which is that gives you the two states. So this was our external potential, and then you have these higher order terms, and the ratio of these two coefficients essentially determines the pattern wavelength. So this is a basic idea. So this is the second row, and I will explain in a second basically why that's important. Now, for paddle system, we basically have a spherical surface underlying, so all these derivatives that appear here are covariant derivatives basically on the surface. And this U basically is a small radial displacement that basically describes the pattern that you see. Yeah? So, good. And whenever I show basically some length quantities that have dimension of length, so they will be normalized by the radius of the sphere. So in general, we assume that this radius of the thickness here of the film, which is h over r, is very small. And yeah, so basically these are the essential ideas. Good. So now just one remark. So this type of equation, when you look at it, so it basically came up much earlier in a very different context. So okay, so maybe just one more thing before I go to this. So just to explain maybe on this slide already why we see two different types of patterns in these experiments. So when you look at this term and you assume this coefficient b is equal to 0, in that case, basically the equation would be invariant by going from u to minus u. So you couldn't basically distinguish whether you're outside or inside. So and this is basically typical of sine solution, for example. So this would suggest a labyrinthine patterns. Whereas if you basically break the symmetry here, with such a term, you get other types of patterns. Yeah. So whenever you break the symmetry of your equation, you would expect something dramatic to happen. Good. And yeah, so this was known basically, as I said, in a completely different system because this type of equation was originally derived for Rayleigh-Bénard convection. So what is Rayleigh-Bénard convection? So when you take a pan and you put in some water and you heat it from the bottom, you will see that hot liquid rises up and then colder liquid falls down. And if you're in the right regime, you will basically see these type of convection rolls. And if you look from the top, you see these hexagonal patterns. And even in these type of systems, you can also, if you tune your system in the right way, you can get this different type of labyrinth patterns. So I think it's quite interesting. So here we see Swift and Holmberg started so in 77, so they derived this equation from Navier-Stokes, so it's a fluid equation. So we start from elasticity theory, completely different system, but we arrive at essentially the same effective equation. Now for our system, we need actually a few additional terms, which are of the same order, essentially u squared here, or u cubed. And the reason we need them is to get quantitative agreement. And I explained briefly that to see a pattern formation transition, we need a symmetry breaking, so which is essentially a u squared term in this equation. So if you look at this term, so it's also u squared. But if you look now at these coefficients here, so because we derived our model from a microscopic model, we know what these coefficients are in terms of the microscopic parameters of the system. So if you look at this B parameter, which is relevant to Swift-Holmberg type Rayleigh-Bénard convection systems, so we see that in our case, we see this scales with the curvature, which is h. So the kappa here is dimensionless curvature. It's the film thickness divided by the sphere radius. So it scales like the third power. So this is a very weak dependence. Whereas this coefficient here, you see, scales linearly. So this coefficient here also has a curvature dependence, but it's also weaker. So to leading order, obviously, we can describe the experimental system just in terms of this effective equation. And that works quantitatively quite well. There's one free parameter, obviously, that we have to determine from experiments. So we determine that from one experiment that's related to this coefficient here. And the pressure that I apply is essentially encoded by this parameter A. So this changes its magnitude as you apply experimentally the pressure. And this is how you drive the system through your phase transition. It's now just how well does it work? So here is an example of simulations, basically, at different regimes, where we change this ratio. So what they can do in the experiment, they can coat the sphere. So basically, it takes the same base radius, 5 centimeters or so, and they coat the system with a thinner film or with a thicker film. And then, basically, you can tune these different morphologies here, these different patterns. So, and this is a comparison with the experiment. And this is a phase diagram. So what you show here is the effective radius, or the inverse curvature. So as you go out here to the right, the sphere becomes large, you go to a flat regime. As you go to the left here, you get smaller spheres. And in this regime, basically, you have a higher curvature. So what you can see here is basically you can drive this transition from this labyrinth phase, from these type of patterns to these type of patterns just by curvature. And in the middle, in between here, there's a coexistence regime. So these lines that I show here, so these are the phase transition lines, those you get directly from the theory. Because so it's something that's quite nice in that case, because we have a Thornberg model, which has been widely studied for 40 years or so. You can borrow their results, and these results tell us something about these phase transition lines, and they nicely determine the data. And I told you there's one free fit parameter, so we can use that fit parameter to say fit one of these lines, but then the other is automatically fixed. So there's not basically a lot of freedom in these things. And also, basically, it's quite remarkable actually that these functional forms fit quite well. So it's basically a power law that you can infer. So we can do quite a few things with this type of model now, just study it theoretically. So we did it basically for more general surfaces. You can look at tori, which are more interesting because they're spatially varying curvature. And what you find in that case is that typically you form these hexagonal pattern more on the outside, and the labyrinth appear on the inside, where the torus is flatter than on the outside, so it's basically qualitatively consistent. And you can also look at topological defects now. So if you're in that regime, so you essentially have a crystal on a curved surface, and you can ask, when I change, so basically reduce the pressure rapidly or slowly, so how many defects do I get? And you find basically that you get universal Kibble-Zurich scaling for these type of things. So we studied these things quite a bit. So basically, this is what I wanted to show you basically in the first part. So in essence, you can start from the energy function for elasticity models and reduce it to basically these type of Thornberg equations, and they allow you then to describe experimental systems. So the second half now is basically a little bit more lighthearted in a way. So it's about basically one-dimensional objects with elasticity and those. Good. So maybe are there any questions about the first part? Yeah, so obviously now it's a reset. So it's
you mentioned in your abstract role of topological defects.
Yeah.
And you could certainly see quite well, not on those, but well, yes, on the right-hand side. But you haven't mentioned them.
Yeah, because obviously I planned for 1 hour originally. So, so what you can do is there are a couple of things. So you can, for example, study these type of equations on like ellipsoids, for example. You can ask, where do I get accumulation of defects? And it happens basically that typically, so if you have a defect, basically that's fivefold, so one neighbor is missing, so those will predominantly occur on the poles.
Yes.
Or if you do it here, basically on these, or look at basically tori in this regime, so you'll find fivefold defects that give you positive curvature on the outside, and you find sevenfold defects and give you a saddle on the inside. So, so the other interesting question is, if you interested in the dynamics of the phase transition, you quench linearly through your phase transition, you see, from a flat state to this external state. So, for example, how does a number of defects scale with the quench rate?
Right.
So, and what you find interestingly, and you can even, I mean, to some extent rationalize it analytically based on this equation, that you get Kibble-Zurich scaling. So, basically, the number of defects scales with an inverse our square root law of your quench rate. And it's quite interesting, and because there's a connection between these elastic systems and some universal phase transition phenomena. Okay, is that good?
Thank you.
I can also afterwards. Okay, so let's go to something much more mundane here. So the spaghetti proper. So what we're particularly interested in is also, we see then in the knot example, is the role of twist in these systems. And so why are we interested in studying one-dimensional system and fracture processes? So here are a few examples. So relevant in architecture, biomedical context, and also material context. If you produce materials that are built from individual fibers, you would like to understand, first of all, what does an individual fiber do? And yeah, also on these materials are more complicated because in friction between multiple fibers and so on. But also on a very microscopic level, so in cells you have these structural events of essentially one-dimensional microtubule structures that are important for rearrangements of the intracellular force network. But we will essentially look at these structures here, the toy model. And that goes back to an old problem. And I'll tell you in a minute how we got to the problem. That was described in this book here. So this is a book that summarizes stories about Richard Feynman, so famous physicist. And one of his friends, Danny Hillis, and I don't know, has anybody heard of Danny Hillis? Anybody used parallel computation at some point? No? Okay. So basically he developed the foundation of these parallel computers. And they were friends, and he had at some point, he had interns, so which included Sidney Brenner, Feynman, Eric Lander, so they were all famous. Okay. So these guys apparently, so they ate spaghetti most of the time when they were meeting, and so one evening they were starting to break spaghetti, and they were just wondering, so why you would always get 3 or more pieces. So that's something you could try maybe with your first spaghetti. If you bend it, so you see how many pieces you get. If you get 2, yeah. So that is a humidity issue, because if you cook spaghetti, you will get you can bend them arbitrarily. So you need dry spaghetti. So it's a problem with the climate here. So it works better. Yeah. Good. Hey, so you can show that this is quite generically the case, and so the explanation for that was actually provided already in 2005, so by Rosalie and Neukirch, and they won an Ig Nobel Prize for that. So Ig Nobel Prize is kind of the diametric opposite to Nobel Prize, but so this is really nice and interesting paper. So the explanation for why you typically get 3 or more pieces, that can be found in their paper, is that when you start to bend the spaghetti and it breaks at the point of highest curvature typically, then as the spaghetti wants to straighten out, it will create a second piece of supercritical curvature. You can hardly avoid that to happen, and it will break again. So you get this cascade. So and they worked it out, and I was yeah, maybe just one example, so that this is also relevant in real life. So this is from the London Olympics. So the guy is fine, and they have a slow-mo, and if you count the number of pieces there, so there are at least 3 pieces in that case. Of course, it's also biased because there's basically one is where his hand is, but it's related to that problem, so that you get these fragmentation cascades. And the question is, how can you control those? Now, I was teaching a class, at MIT, so it's not really typically do most of the time like breaking spaghetti. So the students have to do a project at the end of that class, and there was a mechanical engineer in there, and he heard about the Feynman story, and he asked the question, can we find a protocol to break spaghetti in exactly 2 pieces? So they tried by hand various things, and they came up with a nice idea, and he wanted to write a senior thesis, which was essentially a master thesis on that. So I told him, you have to build a proper device for that. And then Vishal joined. So Vishal is actually here from Cambridge originally, so he went through part 3. And then Norbert and Emmanuel Villamino also helped with the theory for the problem. So this is the kind of setup that Ronald built. So the professional spaghetti fraction device. It wasn't very expensive, so it was below $50, I think, dollars or so. So you can anchor basically the spaghetti here, and then you can clamp them on one end, and you can have a rotary device so that you can control the initial twist angle. So that's the basic idea for this thing. So then we got basically a very high-speed camera for free, so it's 1 million frames per second, which is really fast. So and now, so this is a movie that just shows what happens when you get a single crack. And this movie kind of explains why cracks are still studied, because it's really fast dynamics and it's hard to visualize. You can come up with a lot of theories. So here's an example. So this is in microseconds. Yeah? So you see initially you see this precursor, and then you have a very fast evolution for a single crack, and then the thing separates. So this is not the regime that we're interested in. So if you think in, so the color changes here because one of the ends will go out of focus. So if you think about time scales, so there is this slow nucleation, so you get in crack precursor, and then there's a fast propagation, and then there's a slower separation. But we are interested in why we get multiple pieces, and we want to apply continuum theory, so we're somewhere on this side here now. So basically here. Yeah? So this is what we're interested in. So we can model in this regime these fracture dynamics to some good extent by using Kirchhoff's model. But basically, this just shows really, I would like to re-emphasize, so even with 1 million frames per second, you hardly see anything. So you would go to even higher time resolution to properly study cracks. But this is now still fairly high resolution, so this describes basically the Feynman observation that you get multiple cracks, what happens when you're in a dry climate. And you see that you have, I think, 7 or so fragments in the end, a few smaller ones. And it's really a cascade, so you can, if you look at the times where the cracks occur, so we have the first one, and you have the next two, and so on. But this is now on the scale of milliseconds here. So to develop a theoretical understanding, we use the Kirchhoff model, so it's a standard elasticity model. So you describe your elongated object as a line, and then you have local frame here, and you're interested in the bending and the torsion of these as you apply external load, for example. So these are the Kirchhoff's equation, essentially coupled PDE systems, and they depend on a number of material parameters. And one assumption that we have to make when we simulate these equations, so that you have basically a minimal fragment length. So the reason is that once you discretize your model, so the first fracture happens, and then the end piece will try to snap back, and so obviously it would break again at this point if you don't make that assumption that this is sort of a relaxation. And this is because simply in the vicinity of a crack, so the Kirchhoff model breaks down. So you have to make this additional assumption. But basically when you make that assumption, then you get quite good agreement basically from a theoretical perspective with these experiments, even quantitative agreement, so you can measure all the parameters. And in your simulation you have to decide basically how the rod fractures, and the way you get that is you construct a stress scalar, which you can get in various ways. So here I showed the one that describes the data bed. So you take the strain tensor, and then you take the square, essentially, the trace of that, so that you have a scalar, and then you integrate over the cross-section of your rod, and then you get basically a stress number along basically your rod, and this can be expressed in terms of the local curvature and in terms of the local twist, and then you have here the material parameters that you can measure, and then in simulation, basically you say, okay, if a critical stress value that you have to fit basically at one point is exceeded, then you get a fragmentation and you cut your rod at this case. But this critical stress value is fixed once for basically samples, and then you get for different twist condition and initial conditions, you get basically predictions for how things would fracture. Good, so the essence of all this is that you can define a dimension as lambda that includes the shear modulus, the twist, so which is bleached, then the critical curvature at the point of fracture, the length, and the elastic modulus. And the essence is that if this number is larger than 1, you would expect exactly 2 fragments. So this is the prediction. In the interest of time, you can linearize the problem and this gives you time scales. If you compare those, you get essentially the same criteria. And the key idea is that if you have twist in your system, then you can reduce the energy so that bending waves cannot trigger a second fragmentation anymore. So you distribute your energy between twist and bending. Twist dissipates faster. Let's see if that works. So this is low twist example. So it's 100 degrees, which is quite remarkable. And it's still very high. So but you can actually take a spaghetti and twist it to almost 360. So it's something you can try if you have a second left. So yeah, you can really twist it very hard, and then you bring the ends together, and then it should basically break into pieces. For those of you who got multiple pieces, so now it should work in these. So you can run many experiments with different types of spaghetti. So if you below, so this is your twist ellipse. So if you below basically that above this critical twist, end-to-end twist, so you essentially get two very consistently just two fragments. So if you have fewer twists, basically you get more fragments. Good. Okay, so nice. The end to that story is, so we didn't know that Danny Hillis was still affiliated with MIT somehow, so he somehow learned of our paper, and then he wrote an email to Ronald, who's the undergraduate, and said basically that Feynman and himself basically had tried this twisting to control fracture, but it didn't work. But so he was quite happy, and Ronald was happy to get that email. Good. So now, if you have a code that can deal with spaghetti, so you can also do knots in essence. So this is the last 5 minutes, and I would like to talk about basically joint work with Matthias Koller, and it builds directly basically on the same theory. So now, if you have worked or seen knots here, so I know at least one person who has worked on knots in liquid crystals, so you can find them in all sorts of structures. So Keith Moffat here has done beautiful work, and then William Irvine has done nice experiments, and also theory on knotted vortex lines or vortices in Maxwell's equations, and you can find them in biology and so on. And they've been widely studied. At the end I can show you a movie actually, so this is not fake. So there's a fish that self-knots, so we can show that if we get to that. But there are also, just these real practical knots that we use in everyday life, and there's a lot of empirical knowledge about these. So there are, for example, hitches. So hitches is when you take a piece of rope and you tie it around a rigid rod. That's how you tie your boat, with some tree or so. But and there's a few things known about these type of knots. So it's a really nice paper here. But a lot of them basically about knots is still unknown on a mathematical level. So there's a nice theory we see of curves, yeah? So mathematical theory of knots. But if you think about the physical properties of knots and you want to know why certain knots are better than others, so it's still not very well understood. So that because of the complex interplay between friction, elasticity, and the topology in general in these systems. So typically we try to focus on one or the other, but actually the full stability is determined by all of these. So Clifford Ashley basically wrote a book that summarizes, it's essentially the Bible for knots, and so here's this nice quote here, or statement in there, so that really, so a knot is either right or wrong, and that demonstrates somehow the importance of topology. So these type of questions have recently been studied, again by Odo Lee and also our collaborator Pato Rice, so they were interested in how the friction, for example, changes as you put more and more bindings into these type of knots. But we wanted to consider a more practical problem. So if you want to escape from prison, so what would be the best way of tying two ropes together? Yeah, so that's kind of the question. So if you tie two lines together, so essentially you would call that actually a tangle, not a knot, but we call them knots anyway. This is from a real prison break here in New Zealand. Good, so just to, so you probably all encountered the problem already. So if you take two pieces of rope and you tie them in this way and you pull on these ends, so that knot won't be very stable. That's called a granny knot. Runners also, there's certain, I think, way runner ties his shoes and that is more stable than the other. And we all probably know from experience that this is better than this one. But the question is also why. I mean, it's a could we predict, just by looking at the topology of these knotting diagrams, at least, roughly what the relative stability of these knots is? And so this was a question we were trying to study and trying to relate it to. Good. So now it's nice if you can actually see the stress that goes into these knots. So so here we teamed up with Matthias Kolles' lab. So what they have developed over the last year are fibers that change color as you stretch them. So this is how it looks basically. So here the fibers, so they can do different color ranges. So here basically stretch them. So they're elastic fibers. They're coated. So it's the same color, a similar color mechanism how bugs or beetles produce colors. So you basically coat them with various layers, and as you stretch them, the layer thickness changes, and that changes the optical properties. So the color is essentially a readout for strain in these fibers. So that's basically how we can gauge our benchmark, our simulations. Good. So this is basically just shown here. So at the top we have basically knots from experiments. So this is always the same knot here, and this is the same knot here, and this is in a loose configuration, this is in a tight configuration, and then here we have a simulation where we map the strain onto their color scheme that they give us. And this just basically shows us that our curvature model, basically with some extra friction, which I can talk about later maybe, reproduces the experimentally of the strain pattern. So then we can use this type of continuum model to study basically different knot configuration and try to understand simple rules for when two knots or a knot is more stable than another knot, for example. Good. Here, so here back to these two knots that I showed initially. So we take our simulations and we can essentially make a race. So we apply the same force at the end and we ask which knot is more stable now using this validated code. So what you see, so the first one unties here and this one basically locks eventually and will be stable. And if I run this movie again, if you look at the ends, so there's something interesting that you see. So here, they essentially stay in plane more or less, and the other, they do this, so they can twist out. And it shows you already that twist plays an important role in basically the stability of these knots. So we wanted to come up with a very simple model, that's basically next to last slide now or so. So to just infer from basically a knot diagram what the stability of the knots is. So, and the way you can go about it is, so you look at a projection of your knot, and you choose one, basically an energetically relaxed configuration, and then you choose a projection where you have the smallest number of crossings. Yeah, so you can do that. And then when you pull at the ends, so you have 4 ends, so you have 2 pairs, basically, so 4 pairs actually, where you can pull different configurations. So then it gives you, for each crossing, a force direction, or essentially a force current along each of the 2 pieces of the tangle. So if you have a configuration like this, where you pull, say, somehow at this end and this end, and you have a crossing like this, so you can think of that as right-handed. And it doesn't depend, so you can start from the red, and it's invariant. If you had a crossing like this, so that would give you a left-handed. So now you can ask, so what does in this case happen? So in this case, you try to rotate this one, you see this finger, because you pull this one through. So you put in a twist charge here. If you do this one, you twist in the other way. If you think about now 2 of these being next to each other, as they go in the same direction, you roll them so they won't contact, but if you point in opposite directions, they will lock each other. And that's the basic idea how these twist effects to leading order affect also the stability of these knots. And the way you can capture this is by simply counting these charges if you want to build a topological model and work them out. And essentially you get a ferromagnetic model, Ising model, or a magnetic Ising model with long range interactions. If you think about that, all of these different crossings are coupled with each other. Then you can go back to these type of knots, and so this is a granny knot, and if you basically count the charges, or first draw them in here at each, so you get basically plus, 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 so the average per side will be +1, the variance is 0 in that case, so this is a knot that wouldn't be very stable. But if you look at the reef node, so this is antiferromagnetic, so this is essentially a higher twist energy. So this is one component that determines why certain knots are stable than others. The other one is friction, actually. So how things. So because in the interest of time, I won't talk too much about it. If you have questions, you can ask me afterwards. But the basic idea is if these nearby structures basically go in opposite direction, so you have a large piece of friction there. Reality is much more complicated, so it really depends on contact geometry and so on. But for leading order, you can classify knots in this way. So you can define a phase diagram where you have the crossing number, which basically gives you the complexity. You have this twist fluctuation that I just explained, and you have the circulation. And if you're on the upper right here, then you get more stable knots. So we, and also basically checked a few things here and with experiments, so that worked quite well. So we did basically prisoner escape experiments in a way. So you try the knot, you touch a weight, and you ask when does it untie as you increase the weight. And so and that is all pretty consistent. Just maybe as a last thing, so I promise. So there is really there are knots or organisms that tie knots in nature. So this is a hagfish. One theory is that they do that to clean themselves. But I think there are some interesting problems here. So, I mean, not just in that system, but so what seems to determine the stability of a knot is its chirality to a large extent. So if you constrain somehow into in a plane which this reef knot is, and it's reflected by this twist energy, then your phase space is somehow constrained, and it's very difficult to untie. Whereas if you have the freedom that you can twist yourself out, basically, so you can explore the full three-dimensional dynamics, then these knots are typically less stable. So what I think there are really interesting problems here, and Pedro Weiss, I know, basically has started to study, and also he has built an X-ray, he's bought basically an X-ray tomography machine. It's very expensive, so and just to see what the contacts look like and so on. Good. Thank you very much. So this is what I wanted to talk about.
Any questions? So what's your recommended knot if
so the
you're ready for
escape
from prison?
So the recommended one, I mean, so it depends. So it's if and clearly if you have more time, basically you just make more complicated and infinite material, you make more complicated crossings and so on. Yeah? But what's quite interesting, you have here what's called the hunter and the zeppelin. And actually, so the zeppelin, so if you go to this one, you can see it. So this one seems to be the best one also experimentally. So both theoretically predicted kind of and experimentally. And people, so this one is very common or widely used in climbing already. This is also known, but so people choose these basically based on stability, but also based on experience. So how easy it is, for example, is it to untie it again? So these things. And there are also other questions. So this tells you basically how robust a knot is against untying by pulling. But another important question for climbers is also whether a knot can break and where it breaks. And some of these knots may be more advantageous in terms of untying, but they may break easier because they have more strain into a certain. But I think, I mean, any of these. So it's kind of interesting that, maybe it's not so interesting, but that these simple models basically recover the things that people know empirically, and they give you some additional guidance. But we are talking to climbers actually, and apparently, so nobody really knows in the community why these are better. So and I think twist provides an explanation here. So everybody knows that this one is better than this one, but even the climbing community, they don't know so much why. So I think we see it goes more in this direction. So what we're doing is trying to explain it.
Have you found any, or maybe from the studies that you made, so if you increase the number of crosses, the complexity, do you know, is there some kind of linear growth of how much they can hold, or power growth, or something like that? How much would you expect? The more complex knot you make.
It's difficult because I think one thing that we learned just from this type of phase diagram, so you cannot simply characterize in terms of one quantity. Like just the number of crossings is not sufficient.
But if you take the maximal for given number of crossings, take the most stable one and then increase the number of crossings or something like that.
Yeah, I mean, so we haven't done that systematically yet. So I think it's definitely nonlinear at some point. So this is one statement I would make. But
how do you define topological function?
yeah, so that's basically so when you apply in the simulation the weight, so then it depends a little bit on so you can think of that as a critical force, right, unties, or in some cases in the simulation you can tune the system such that you get a sedimentation speed,
Right.
where you look at given an applied force, how fast does it?
Yes.
And
so perhaps a related question, you had these beautiful pictures of the colours exposed during the in the knot. Are they reflecting extensional stress or the bend, the local intensity of the bend?
so I think in many of these cases it's bending dominated. So we plotted the relative strengths, I mean in simulations. So and I think it's mostly due to bending because you see, for example, here, so you get these high curvature regions where they.
Yes. That too would affect friction, of course, because
yeah,
a force on a curved object is a perpendicular.
Yeah. No, I agree. So the way we went about it, so we tested simply various friction models, and then went with the results that were robust against variation in those. But what I already said, so the actual contact, the shape of the contact is very important to really understand, but that gets very messy very quickly.
Yeah.
So I think there's one result by what is his name? So he's also EPFL. So he shows if you just take two lines and you put them like this, so you get a polygonal contact because you have 4 contact points. So now once you start to, and that's what Pedro has already measured with his X-ray machine. So it's really in real knots you see that there are these leading orders, these 4 contact points, but then there are distributions around those. Now once you start to get displacements like this, so then things become very complicated very rapidly. So it's a highly non-trivial problem to really understand mechanical properties of knots like in detail. So which is why we focused on these topological things, which are very coarse, but they give you a rule of thumb. For example, why the greave versus or the granny versus the reef knot are more stable. But I mean, these simple topological rules or Ising models, they never capture everything. Questions?